and we'll get started. Can everyone see the funky looking graphs on the screen? Can everybody see the funky graphs on the screen? Yes, excellent, wonderful. Okay, super duper. And let's see here. We're obviously going to start talking about polynomials today. And you've already done polynomials in Algebra 1. So why in the world are we doing polynomials again? Well, because polynomials are huge in terms of getting all of the information you need for SAT, ACT, all that kind of stuff. So with that in mind, we're going to need to make sure that you fully understand everything about polynomials so that we can then tie it to geometry. Okay, can you guys see my pen? Yes or no? Yes, okay, so you can see the doc cam, okay. All right, so if I have something that looks like this, this is a straight line. This would be considered a linear equation. Linear equations are y equals mx plus b. You got your slope, you got your y-intercept. So you're all good there. It's no biggie. So you got slope, you got y-intercept. Then, if I were to take something a bit more complex, so for example, if I have somebody standing here and they throw a ball like this, what's going to happen to that ball once I've thrown it? What's going to happen to that ball once I've thrown it up in the air? Put it in the chat or say it, heaven forbid. Oh my gosh. Yeah, it's going to come back down. It's going to fall down. Yep, that is exactly it. And so that ball is going to do this. It's going to go woo like that. And so that is clearly not a linear equation. It's not a straight line. In fact, what it is it is a parabola. And a parabola is a quadratic equation. Now, you're familiar, or should be already, with the quadratic equation from Algebra 1. X squared, so ax squared plus bx plus c, that is a quadratic equation. So in this particular case, we would say y equals, and I don't know, it would be something like x minus 25, quantity squared with a negative here, plus, I don't know, 30, something like that. And when I put it all together, I FOIL it out, I'm going to get x squared minus 50x plus 625 plus 30, but that has a negative out front, so y equals negative x squared plus 50x minus 625 plus 30, so it'd be minus 595. So that would be the equation of that graph right up there. So in this case, you have linear, you have quadratic. This you should have already seen. This you should have already seen. This you should hear, because if nothing else, we have quadratic equations and quadratic formulas. Now, additionally, we can have other things, because if I have x to the first here, and I have x squared here, obviously, what do you think is next? If I have x to the first, x to the second, what's going to be next? Well, x1, x2, so x, there you go. x3. And so a cubic function is going to look like this, x cubed. Then after x cubed is going to be x4. Then we have something like x to the fifth, x to the sixth, x to the seventh. And so all of these are going to keep going on up and up and up. So I have x to the 5th. I have x to the 6th. X to the 7th, and so on and so forth. It keeps going just like that. And so we have odd functions. Why are the ones that I just circled odd functions? Why are the ones that I just circled odd functions? Put it in the chat. Odd numbers. Yes, the powers are odd numbers. So it doesn't matter if there's a -1 out here, a -4 out here. It's a matter of what's the power. So if those are odd functions, then obviously squared, fourth, sixth are considered what kind of functions? Even functions. Even functions, that's right. Sorry, I had a student question here. All right. So we have those. Now, what we want to do is we want to say, well, why do I need all those funky shapes of different graphs? Well, because we see all sorts of funky shapes of different graphs in real life. In this particular case, we're looking at existing home sales and forecasts. So the blue would be home sales from 2000 to 2016. Then you have the two red bars, and the red bars are the forecast for what they think the housing was going to do. Now, very quickly, I want you to keep in mind, because I'm going to ask here in a little bit, how do you think they got the height of 2017 and 2018 when this graph was made in 2016? How come these bars are this height? How come they're not low? How come they're not high? Think about that. Now, in this particular case, while you're thinking about that, let's draw some stuff on here. First things first, if I tried to draw a straight line on this graph, does that straight line look like it follows the path of the graph? Yes or no? Does this red line? No, it does not. Of course not. Okay, so what if I tried drawing like an angled line? Does that fit better? Does that fit the graph better? Not really. You'd say, well, I mean, it may fit this part better, but it doesn't fit this part very well. Or vice versa, I could make it kind of fit this part, but then it's just way off when it gets down here. So we need something else. If, on the other hand, I'm allowed to use a curved line, now that curve doesn't exactly hit the top of all of the bars, but is it closer than any of the straight lines? Yes or no? Yes. Now my question to you is, which type of equation does this red line look like that we've taken a look at? Which one of these red lines does it match? Linear, quadratic, cubic? Well, actually, yeah, cubic looks pretty good. Now, obviously, if I have this stood straight up, this cubic that I've drawn here is way more up and down than this cubic, this red cubic line. But here's the thing. could I just as easily continue my drawing and really make it look nice and cubic? Well, yeah, we can totally make it look nice and cubic. And so what we have is we have this cubic function right in here. And so we would say some version of an x cubed would be a good estimate for this graph. Now, back to the question I asked earlier. Where did they get the height of these two red bars? How come they didn't make those two red bars like up here, or make the two red bars way down here? How come? Put it in the chat. How come these red bars were made about this high and this high? Estimated from the years before data. That's true. So they look a lot like these years, but how come they didn't make them like shorter down here like these data, or up high like these data? Well, the idea is whether you're using a straight line or a curved line, it's a line of best fit. In our case, we used a polynomial to best fit this data, okay? So we use it to best fit that data. Now, let's take a look and let's do this graph down here. This graph is not quite as easy because we have stuff all over the place. And so we're going to have to take a look. Now, in this case, it's rental or retail shops rents. So the gray in the back is how much rent a shop has to pay. This gray line is visitors that are arriving at a destination. So the number of tourist arrivals. And then the red line is the amount of retail sales, which means how much are they selling? All right, so let's take a look and let's figure out what the best type of estimate is for these graphs. Now, for this red line, tell me if I do an okay job for the red line. Is that one broadly okay? Does this red line match as best I can these other red dots? Yeah. Now, in this case, I could draw it up and it would probably go on down. Again, we go down, up, down. And does this show you a pattern a little bit better than the crazy stuff that's going on otherwise? Where do you think in 2022, where do you think the retail sales will be? Up here, in the middle, or down low? High, middle, or low? High, middle, low for 2022. Because remember, this is 2018, this is 2019. Where's 2022 going to be? Up here, in the middle, or down here? Low. I would agree because it looks as if it's headed down. Looks as if it's headed down here somewhere. So it's probably going to go low. Now, how come you can't guarantee that 2022 is going to be down here like this? How come you can't guarantee it's going to be down there? It is an estimate. Very good. And did it turn around here before? Because it looked like it was going down, but then it came back up. Now it's going down. So what else might it do? Might it go like this? Oh, it might stay the same. Yes. Maybe it levels off. That's a good question. Maybe it levels off. Maybe it stays the same. All right. Or could it theoretically go back up? Well, sure. It could. We don't know. That's why it's an estimate. And I think that's a great word you used. It is an estimate. Once you get past the actual known data, we're just estimating. And you could make a good argument for this blue line, or you could make a good argument for the red line. We simply don't know. What we do know is that a straight line would be a pretty bad estimate of what's going on this graph. If I tried doing this number, that doesn't match very well. That doesn't match very well. That doesn't match very well. And so none of the straight lines are going to work. That's why we're going to have to be able to work with polynomials. Now, real quickly, let's go on to this. This is what's called a polynomial regression. A regression is something that they simply average the values. But now we're going to use one polynomial to be an average of different values. So let's take a look at this guy right here. In this case, we have a glass vase. And that glass vase, we are trying to use these little dots to estimate. If I only use a straight line to estimate, that means when I rotate that straight line around, I get this shape, which technically would work as a vase, but it's not going to look very much like this vase here. On the other hand, what if I give it a cube? There's a cube. Does that look like the vase? Well, it's at least rounded some. Fourth, that doesn't really look like it at all. Fifth, hey, look at fifth. Fifth, we're starting to get closer, but the bottom is way too big. So maybe we keep going up an eighth power, we're getting better. So here we go, let's crank it. We get to 13, we get to 12, we get to 11. They're looking pretty good here. Let's go ahead and crank it to 15. And you'll notice these little dots, the 15 key points, match the vase pretty well. So that when I slide this one around, it actually does look pretty much like my vase. So as you can see, our vase, when I rotate it around using our estimate, is really starting to look pretty good. This is exactly what happens when you do CAD drawings and you have computer-aided machinery. It allows you to define real shapes in terms of equations. And so by using equations, it allows computers to create the same parts over and over and over again. So another example of kind of what we're talking about here is we can break up a different shape into different chunks And by changing the widths of those chunks, we can go from something that's squared to cubed to fourth to fifth until it really gets us looking very solid here. Okay, so just to give you an idea of where polynomials are used. Now, let's move on to what we actually need to talk about. This is actually returned to Algebra 1. And so in Algebra 1, you learned about polynomials. And the polynomials that you learned about were things that look like this. 3x to the fourth plus 2x cubed plus 3x squared plus 2x plus 5. Something like that. So let's put that up on screen. Okay. Now, with that in mind, what we can do is say y equals. Now, we could also say it's a function. F of x equals 3x to the fourth plus 2x cubed plus 3x squared plus 2x plus 5. If I want you to evaluate, that's a key word, evaluate at x equals 3. One way I could say that is f of 3. Now, folks, if I want to know what the answer is when x is 3, what would I do to figure out what the answer would be when x equals 3? If here's my equation and x equals 3, how would I find what y equals? Put it in the chat. If I have the equation, I know x equals 3, how can I combine these two to figure out what y is? I'm going to go ahead and plug it in. So what I could say is I could say 3 times 3 to the fourth plus 2 times 3 cubed plus 3 times 3 squared plus 2 times 3 plus 5. And I could go through here and I could say 81, so 243. Then I got 27, 27 times 2, 54, plus 27 plus 6 plus 5. And if I put all these together, that's 97, 297, 97 plus 20, 324, 330, 335. And so if x equals 3, y equals 335. Unless I made a mistake. Okay, so all I had to do was take 3 and plug it in. Another way to say it is f of 3. That means instead of putting in x's, I put in 3's. So 3 times 3 to the fourth plus 2 times 3 cubed plus 2 times 3 squared plus 2 times 3 plus 5. There you go. And so f of 3 equals 335. There you go. That's a polynomial, and that's evaluating a polynomial at a point. All that means is if I have some sort of graph and I want to know what is it at 3, it's going to be way up here, 3, 335. That's what it means. So I can look at a polynomial as a graph. I can look at a polynomial as an equation. And I can evaluate that polynomial at a point. All of these things you should have done in Algebra 1 as far as simply understanding what is a polynomial, how do I plug in a value for a polynomial. Now, you probably didn't do any this big. You probably did some that are significantly smaller. So let's do another example of one that's smaller. y equals 2x squared plus 4x plus 5. This is one you should have done in Algebra 1. And so f of x would equal 2x squared plus 4x plus 5. And if I wanted to know f of 1, what would I do to figure out f of 1? Somebody tell me, how do I find out f of 1? How do I find out what this function is when I plug in 1? What do I do? Put it in the chat. Okay, going to plug in the values. And so 1 squared is 1, 2 times 1 is 2, 4 times 1 is 4, plus 5. Answer is 11. There you go. Answer is 11. Now, with that in mind, we need to talk about a few vocabulary words. The vocabulary words we have term, we have powers, we have coefficients, we have leading coefficients, all right, and so in this case, let's talk about it. How many terms do I have in this equation? The number of terms is 1, 2, 3. There are 3 terms because there are 3 pieces. Yeah, put it in for x. Very good, Isabel. There are 3 terms because there's 3 pieces separated by plus signs. The powers. Now, I got a power here. It's a power of 1. But the highest power I have in the whole equation is 2. So it's to the second power. And a second power equation would be considered quadratic. That's its fancy name. Coefficients are the numbers in front of the x's. So 2, 4, 5. So the coefficients here are 2, 4, 5. And finally, the leading coefficient is the number that is all the way up front of the highest power. Up front of the highest power. And so that would be 2 because it's in the lead. Now, here's the question. I need to know how many terms are there in this equation right here? What is the power of this one right here? What are the coefficients of this right here? And what is the leading coefficient of this right here? So, in this particular case, how many terms? 5 terms. What's the highest power? Well, there's a 1, a 2, a 3, a 4. Highest power of 4. What are the coefficients? 3, 2, 3, 2, 5. The leading coefficient is 3 because it's attached to the x to the 4th. You wouldn't say 3x to the 4th. You would just say 3 because it's just the number we're interested in there. All right, so polynomials, poly meaning many, 5 in this case, 3 in this case, many terms. So polynomials. And you need to know some of the basic vocabulary that goes along with them. By the way, last question, is this function here, this x equal or y equals 3x to the 4th plus 2x cubed, blah, 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 is this an even function or an odd function? Put it in the chat. Is this an even function or an odd function? Ooh, it is an even function because we're looking at the power, and the power is 4, making this an even function. Now, the number out front is odd, but remember, the number is just a coefficient, not a power. So it would, in fact, be even. Okay, so that is what we have for today. Let's go ahead and take a look at the slideshow. So we've talked about this slide, we've talked about this slide. Polynomial introduction, you need to do these 2 ed puzzles right here. Don't do the problems, homework problems listed. We will talk about them together. Then you can start working on polynomials, so classifying them, rewriting them in standard form, finding coefficient, doing vocabulary. Well, gee, that's the same stuff we just did today together. So that shouldn't be too much of a problem. And so what we can do here is you need to have these done. And of course, where do you turn them in? The one labeled polynomial introduction. And it's due on Friday. When I see all of you tomorrow, in class, we will talk about addition and subtraction of polynomials. And that will be due on Monday. And monomial multiplication, also we'll talk about that, due on Monday. And you can see that we are off and running. Do not, ladies and gentlemen, wait to do your homework. Please get off to a good start. Please start early, okay? So get going on this stuff, get it done. You have basically 30 minutes left of this class. Honestly, in 30 minutes, you should have this slide done, and you should have started on this slide right here, and you're already ready to go. So with that in mind,